Hello. First of all, let's make an adjustment. We are not actually going to reach the binomial theorem here, but we're going to be talking about binomial expansions. Binomial, of course, is a word that means two nomials, two terms. So we're thinking about x plus y raised to different powers. And I've done all the algebra for you here. X plus y to the 0 power is just 1. X plus y to the first power is 1x and 1y. X plus y squared, you know how to do. That's x squared, 2xy, y squared. But what happens if you keep going? There are a lot of patterns that you might notice in this table. There are patterns to do with the coefficients. There are patterns to do with the powers of x and y. And maybe patterns is even the wrong word. There's just lots of things to notice, just facts, peculiar facts. So go ahead, pause the video, or if you're doing this in class, let's talk about it in class. What are all the things that you notice about things in this picture? Okay, so lots of things to notice. So let's look at the x plus y to the fourth row here. So one thing you might notice is that the highest power of x is 4, and the highest power of y is 4. So you don't ever have an x or a y that's a higher degree than 4. You might also notice that if you add the powers of x and y, they are always 4. X squared and y squared, 2 plus 2 is 4. X cubed, y to the first, 3 plus 1 is 4. X to the fourth, and then you can think about this as y to the 0, 4 plus 0 is 4. And that seems to hold true in the other rows also. So that's one fact to be explained. Another thing that you might have noticed is every combination of integer powers is present. So we start at x to the fourth, and then we go to x cubed, x squared, x to the first, x to the 0. Meanwhile, the y's are compensating. So it's not just the case that when you add the two powers, they add to whatever this exponent is. It's that all possible sums of that kind are present. Somebody last block noticed that when the exponent is 4, there are 5 terms here. When the exponent is 5, there are 6 terms. What else is to be explained? So somebody noticed that if you look at two adjacent coefficients, so 6 and 4, they add up to give you the coefficient that happens right between them in the row below. So 3 plus 3 is 6, 1 plus 4 is 5, and so on. And you might have heard of a thing like this called Pascal's triangle. So if you only looked at the coefficients, you're right, they form a kind of a Pascal's triangle. You can kind of look at this like a triangle. Once you're looking at it like a triangle, if we draw a line down the middle, you might see that there's a kind of a symmetry here. The powers of x and y aren't symmetric, because here we have x cubed and here we have y cubed, but the coefficients themselves are kind of symmetric around this middle line. So that's a lot of stuff to explain. I'm going to write down our list of mysteries to explain here. Meanwhile, you should try and use those facts that we've observed to write out the full expansion for x plus y to the 6th without doing any algebra at all. A nice trick for making sure you fit in the triangle here is underneath each term from the previous row, write a plus. That'll give you kind of the right spacing for the terms that you're about to write. Okay, so I have written down the mysteries. Why isn't there a power of x larger than the exponent? Why do the powers of x and y always add together to be the exponent? Why is there a reflection, symmetry in the coefficients, and why is there this Pascal's triangle addition pattern? Let's go ahead and fill this out. So if I'm going to kind of follow the pattern I see here, I've got x to the 6th, x to the 5th y, x to the 4th y squared, x cubed y cubed, x squared y to the 4th, x to the first power, y to the 5th, and then y to the 6th. And then for the coefficients, let's do a 1 over here and a 1 over there, because I'm seeing it's kind of 1s along the edges. And then we'll do the addition. So 1 and 5 is 6, 5 and 10 is 15, that's 20, and then because it's symmetric, or using the addition again, we've got 15, and then 6. Great. So not too bad. So if we want to explain where these patterns come from, a nice approach in math whenever you're trying to explain anything is to think about the process that generates them. So if you were thinking that the main lesson is answers to these questions, that's not quite right. The main lesson is the process, the discovery process that would let you discover the answers to these sorts of questions. So let's take a brief digression here and think about the process of expanding things that are multiplied. So zooming way back to algebra 1, if I have x plus y squared, that's the same thing as x plus y times x plus y. Despite being objectively worse, a lot of people still use FOIL. What's it worse than? It's worse than the area model. The area model is objectively better. But FOIL is a kind of misguided acronym that tells you an ordering that you can use to multiply these things together. The F stands for multiply the first things together, so that's x times x. And then the outer things, so x times y. And then the inner things, y times x. And then the last things, y times y. Okay, there's a lot of reasons FOIL is silly, but one of the main reasons FOIL is silly, well, one reason FOIL is silly is because FOIL does not extend cleanly if I was going to add another term here. So what happens if you have x plus y cubed, x plus y, x plus y, x plus y? FOIL doesn't have anything to say about that. Another thing that's silly is it implies that there is a particular order you should do your multiplying in. Like you've got to do this first, and this first, and this next, and this next. But obviously that's not true. I could have done this in any order. I could start with these ones, and then do those ones, and then do these ones, and then do those ones. So there isn't a particular ordering. Here's the big takeaway. If you want to know what is the process of expanding any binomial raised to a power, all we're doing is we're writing down all possible ways of choosing one thing from each group to multiply. So look here. Like think about that sentence again. And if I were in class, I would tell you to tell your neighbor, in what way are these four terms all the different ways of choosing one thing from each group to multiply? How do you see that? And now, because it's just me here in the empty classroom, I will answer the question. So this is systematically picking each thing that can be multiplied by this x with each thing that could be multiplied by this y. So if I choose x, I could multiply by x on this side. If I choose x for the first one, I could multiply it by y on this side. If I choose y on the first one, I could multiply it by x on this side. Or if I choose y on the first one, I could multiply it by y on the second side. So that's systematically multiplying each thing from here by each thing from here. So now if we were going to do that same thing over here, I could do it in an unsystematic way because there's no reason to order it. The only danger is I might miss one. But let's just like randomly choose one thing from each to multiply. So I know when I multiply this out, I'm going to have a term that's x, y, x. And I know that I'm going to have a term that's x, x, y. And I know that I'm going to have a term that's y, y, y. And I know I'm going to have a term that's y, x, y. And now I'm getting worried because I don't want to repeat myself, but I also want to make sure I'm covering all of them. And so that's why it's sometimes better to do a systematic approach. So now I'm going to do a little bit more systematically. So I could choose x from each of them, or x from the first two and y from the last one. Or y from the second one. Yeah, let's do this one. Let's do x from the first one and all the possibilities there. So x from the first, x from the second, alternating. X from the first, y from the second, alternating in the third. And that's all possibilities when this one is x. And now I can just repeat all four of those possibilities when I've chosen y as the thing to multiply from the first one. So I'm just going to copy my same table here. So that's 8 total possibilities, and that covers all the possibilities. And, using your good combinatorics thinking, you might think about why is that true. Okay, digression over. So I said a lot of words here. What was the one big takeaway? Think in your mind, what is the one sentence takeaway about what does it mean to expand a binomial? So I haven't arrived at the best way to say the sentence, but you're multiplying everything by everything. So you are multiplying all combinations of the elements. Or maybe this is the best one. You are writing out all the different ways of multiplying one thing from each group. So this 8 terms is all the ways of multiplying one thing by each group with each other. Okay, so the question is, how does that insight help us answer these questions? I'm not really going to say that much here, because I think you can answer all the questions. So if I've got x plus y to the fourth, we have all our same questions about these. What creates these coefficients? Why is the sum of the powers always equal to 4? But to answer those mysteries, think about the process that generates these terms. I'm doing x plus y times itself 4 times. This is systematically writing all the ways of multiplying one thing from each group with each other. And to take this and simplify it up here, of course, I group them by like terms. I think that's the phrase from Algebra 1. So I observed that yyxx is not different than yxyx, because order of multiplication doesn't affect the product. And so once I've grouped them, that's what gives me this. Okay, so you keep looking at this page. Right now, see if you can give nice, clean answers to as many of these questions as you can. Go. Okay, so hopefully this made the mystery of the pattern in the powers pretty clear. So question 1 was, why isn't there an x to the 5th? And the answer is, because the process that generates these terms requires that we choose one thing from each group, and there are only 4 groups. So it's never even possible to choose 5 x's, or 5 y's for that matter. Okay, why is it that adding the powers always gives you the same product, the same exponent here? Exact same reason. I'm choosing one thing from each group, and so if you ignore which thing I've chosen, I'm always choosing 4 of them. A different way of thinking about it is someone from last block said, think about this as always being a power of 1. So x to the first, x to the first, x to the first, x to the first. So clearly if you simplify that, you end up with a 4th power. But you can't combine x's and y's with each other. But if you combine them separately, you'll see they should still end up being 4, because at the end of the day, you're still just multiplying 4 things. So, mystery number 2, resolved. What can we say about coefficients? Well, before we can start explaining patterns for why do certain coefficients add to the other coefficients, I think it might be helpful to think about, well, how could we predict what this coefficient is based on the process that generates it? So let's, sometimes when you're stuck, it helps just to ask yourself a question out loud. So here I'm saying, all right, why 6? Why is this 6? Well, it's 6 because there are 6 of these. Well, wait, what are these? Right, so the process that generates these, I'm finding all the ways of multiplying 4 things together. So this must be all the ways that I can end up with an x squared and a y squared. So why are there 6 ways to end with x squared, y squared? That's the question. And again, you might have heard this sounds like a combinatorics problem, because I'm saying how many ways could something happen. So that's what I want you to talk about right now. How many ways, like why is it that there are exactly 6 ways to end up with x squared, y squared? And a good way of testing your idea is down here. Let's apply it to a larger case. Let's pretend we're doing x plus y to the 20th. So I'm multiplying 20 things, 1 thing selected from each group. Eventually I'm going to end up with x to the 8th power. What's the y term, and what's the coefficient, and how do you think about it? And that will be the end of the puzzle. Okay, here's the answer. So if x to the 8th power is happening, what that means, this term is coming from all the ways we could select 20 things from these groups to multiply. So if 8 of the things are x's, then that must mean the remaining 12 of them are y's. So that should be x to the 12th. Okay, how many different ways could I end up with 8 x's? Well, I could have chosen my first 8 things to be x, and then the last 12 things to be y. Or I could alternate x, y, x, y, x, y, but then I'll run out of x's, and then I'll have just y's to end with. Or maybe I could have started with y, 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 x, 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 y, 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 like that. So there's a lot of different orders that I could have chosen from. So if I'm asking how many ways could I have ended up with x to the 8th, I know exactly 8 of these 20 things need to be x. So if I have 20 things, I am trying to choose 8 of them to be x. Because remember, this is saying what are all the different groups of 8 that are possible when selecting from 20 different things. And that's the answer. So the coefficient here is just the number 20 choose 8, because that's saying how many ways could I have selected 8 x's from the 20 things that are getting multiplied. If you're thinking, another way to think about this is, could I have chosen the y's? And the answer is absolutely yes. I could have said, how many ways are there to select 12 y's out of the 20 things? And these are the same number. And you've already had 2 problems and problem sets leading you towards the idea for why intuitively should these be the same. So now is a third opportunity for you to think about that. Okay, that's it for today. we've had a lot of useful thoughts about why do you see these particular patterns when you expand binomials. What haven't we explained yet? We haven't explicitly explained why do we see this reflectional symmetry in the coefficients, although maybe you have an idea about this. We also haven't really explained why is there this addition pattern in the coefficients. And so that's going to be next time, is explaining those two things and getting the theorem back in the binomial theorem.